So I think we can begin. Our next talk is Maciej Ulas from Krakow, who speaks on equal values of partition functions via Diophantine equations. So,
thank you very much. Thank you for the possibility to give this talk. And I will speak about my joint work with Szabolcs-Tengeli, and the title of my talk is Equal Values of Partition Functions via Diophantine equations. So let us start with short plan of the presentation. I will start with some introduction and motivation. Next, I present some first results concerning the topic. Next, I present some other results concerning the general functions, partition function concerning related to the set A equal to 1 to 2, and some related equations. And finally, at the end, I will state some questions and conjectures which I believe may stimulate further research. So for me, n is a set of non-negative integers, n plus is the set of positive integers, and self-explanatory notation n greater or equal to k is the set of integers greater or equal to k. So let A be a subset of positive integers and take n in n, and then by a partition lambda we mean with parts in the set I, we mean the representation of n as the sum lambda 1 plus as lambda k, where lambda I belong to the set A. So the representations of n with differing only in order, the terms are counted as 1. So we can consider the set of part A n, which just consists all A partitions of n, and then we can consider the corresponding partition function, which is just the power of this set part A n. And as we know, one can easily compute the generating function of this sequence PAN, because it is finite, and we have this formal identity. But essentially, if we assume that modulus x is less than 1, then this equality is also makes sense in analytics sense. But for our purposes, this is not important now. And the famous partition function of Euler, we get it by for A equal to n plus. And this, as I said, this partition function was introduced by Euler and then extensively studied by Ramanujan. Okay, so generally, the one of the central problems in partition theory is to obtain partition identities. So what does it mean? So if we have W is a certain property which can be applied to the parts of a given A partition, lambda of a positive integer n, then we can count the partition A partitions of n having this particular property lambda. So by partition identity, we mean an identity of this form for certain sets A1, A2, which are a subset of n plus, and certain properties W1, W2. What is important that we have the same number here and here. So the basic identity of this kind is Euler's identity, which says that the number of partitions into odd parts is equal to the number of partitions into distinct parts. So here we have the sets A1, A2 are equal to n plus, and we have appropriate properties W1 and W2. So much deeper properties, much deeper identities are Rogers-Ramanujan Tyben identities, and the simplest in the whole infinite family of identities of these kinds are this one picture on this slide. So for example, the first one says that the number of partitions of n such that the adjacent parts differ by at least 2 is the same as the number of partitions of n such that each part is congruent to either 1 or 4 modulo 5. And similar interpretation can be given for this second identity. However, according to my best knowledge, nothing or almost nothing is known about identities of this different form, where we allow that n and m are not necessarily equal. Essentially, and of course, we are interested in real equalities which are non-equal to 0. Both sides are non-equal to 0. So yeah, so with this approach, we are interested in non-trivial identities, because this is important, because if the set of values of this partition function contains all positive integer for some I, then the problem is trivial. So for example, if we take A1, this is the set of powers of 2, and say the property W1 says that at most 2 parts in A1 partition of R are equal, then if we denote this partition function by Sn, then we have this identity, this generating function for our sequence of counting partitions of this type. And this is quite famous Stern sequence, which satisfy the recurrence relations of this type. And moreover, one can easily prove that in this case we have that the number of partitions of this type of the number 2 up to n is equal to n plus 1. So essentially this sequence contains all positive integers, and the question concerning the solvability of this equation 1 is trivial. Okay, so essentially this kind of this question can be seen as living on the intersection of discrete mathematics and Diophantine equations. And so, because we are unable to get some general results, it is quite natural to start our investigation with the case when the set A is finite. So this is, I believe, is quite reasonable due to the fact that PAN, so our function counting A partitions where A is finite, is so-called quasi-polynomial. So more precisely, if we have, if our A is just the set A1 up to AK, and we define the latest common multiple of the set of these elements A1, A2 up to AK, then the partition function PAN along this arithmetic progression is just a polynomial for I equal to 0, 1 up to Li minus 1. So this is if A1 and A2 are finite sets, then essentially the solvability in positive integers of our equation 1, this one, is equivalent with the studying of the sets, finite set of some equations of this type where I is in the set 0, 1 up to Li1 minus 1, and J is in the set 0, 1 up to L2 minus 1. So essentially for A1 and A2 finite, we need to consider a quite big number of equations in order to get definite result. So, but if this is a polynomial, this is a polynomial, so essentially we enter into the world or realm of polynomial Diophantine equations with so-called separable variables. So this means that on this one, on this side we have one variable, on this side we have the other variable, and we can try to use a machinery from Diophantine equations. Okay, so first easy results is that is the following, that if we have the set A containing only two integers, A1 and A2, then essentially we can take any polynomial and in fact any function which takes infinitely many positive values, and prove that this particular equation has infinitely many solutions in positive integers. So this is easy because we have a nice formula for the partition function in this particular case. This is one on many equivalent forms of this formula. Here, AI prime is just the solution of this congruence under these conditions, and here a plus 1 is taken modulo 2. So generally we have that this partition function, this takes this value or this value plus 1. So if we take n equal to a1, a2, fm minus 1, when and m is chosen in such a way that this condition is satisfied, then one can easily compute that ai prime is just a plus I plus 1. So this we have this kind of identities, and then we get what we need. So this is quite simple and general, but unfortunately we are unable to get something more general, for example, for general set containing 3 integers, but not all is lost, and we can prove something like that. So let us take an is just the set of consecutive integers 1 up to n, and in order to simplify the notation a bit, we define p and x is just this partition function counting representations of integers as the combinations of elements of this set. And then we can prove that the Diophantine equations p3x equal to p4i y has infinitely many solutions in integers. And in the case when we play with the set containing 5 consecutive integers, then this equation has only finitely many solutions in positive integers, and they can be enumerated. And here is exactly the set of solutions. So let us sketch of the proof. Again, we need some formula in order to play with this equation. We need some kind of formulas, and one can compute work modulo 6 in case of the P3, and modulo 12 in case of P4, and obtain some concrete polynomials in variables n, and then essentially we need to solve some type of Diophantine equations of something like a polynomial of degree 2 equal a polynomial of degree 3, and similar in this second case. And altogether we need to solve 54 equations. And what is important, that in each case we play with the equation of the type y squared equal to fx for some f polynomial with integer coefficients, and the degree of f is 3. So for example, if we consider this equation, which can be written in this form, then after necessary simplifications and substitutions, we need to solve this equation, which represents an elliptic curve. So elliptic curve, we can compute the rank, we can compute the torsion, we can compute the generators. In our case, the rank is equal to 2, and generators are here. And using more or less standard methods of finding solutions of these type of equations, we can prove that all integer solutions are presented here. And of course, not all are good for our purposes, but only this one P1 and this two P2. And in this particular case, we have only two solutions, which lead to these equalities. And case-by-case analysis reveals that the solutions exist only in the following cases. And here we have the table containing the precise description of the all solutions of our equation. So we have along some arithmetic progressions, we have only finitely many solutions. Along other, we have infinitely many solutions which are parameterized by polynomials which take positive values. And essentially similar approach can be taken in this more difficult equation P3x equal to P5y. And then we need to play with 360 equations, and of course doing this by hand would be quite difficult, and then we use the computer in order to reduce the number of cases to consider due to modular constraints or something like that. Okay, so we have seen three easy results, and what is important that in order to get something non-trivial, we really need to have precise description of our function. So precise in the sense that we have a concrete polynomial in each case. So in general, this is quite difficult to obtain the full descriptions of the corresponding polynomial for variable values of elements of the sets. But in some cases, it is possible. For example, if we take the set A equal to 1, 2, and A, which is greater or equal to 3, then we can compute a precisely the shape of the polynomial. And here is the shape of this polynomial. And this is important because we know the coefficients of this polynomial, and then we can try to use these coefficients to get some results. And for example, having this description, one can prove something easy. For example, if A is even, then we have identity of this type. This is trivial and can be proved combinatorially. But still, we don't need to think about the history and work too much to get this result. And for example, if A is odd, then there are only finitely many values of n such that PAN is equal to PAN plus 1. Other result is a bit more interesting, I believe, that says that something like that. If A is not congruent to 2 modulo 4, then this Diophantine equation PAM equal to P4N. So P4 is the number, this is our partition function counting the partitions into parts 1, 2, 3, 4. Has infinitely many solutions in positive integers. This is quite interesting, I believe. And if A is congruent to 2 mod 4, then this equation has only finitely many solutions in positive integers. So it would be really interesting to have a combinatorial explanation for this fact. And similarly, we can prove that there are infinitely many squares among the values of this particular partition function, which is quite typical in the area of Diophantine equations. And moreover, if under some small assumptions on A and B, one can prove that these partition functions has infinitely many common values in positive integers. Okay. So there are some results, and now I will skip to the last part of my talk and ask some questions and state some conjectures. So quite natural question is the following. We fix integer k, positive and greater or equal to 2, and have some polynomial f. And the question is whether we can construct sets A2 equal to A1, A2, and so on, up to AK equal to A1 up to AK, such that the Diophantine equations of this form, so we want to know whether the partition function related to this AK has common value with the values of the polynomials f, and we want to have at last CKF solutions in positive integers, and moreover we want to have this constant going to infinity with k. This is important because if without this condition the problem is easy, because as we know, if we take A2 equal to A1 A2, then we know that this particular equation has infinitely many solutions, and then we can choose A3 as big as the smallest integer n, such that there is at last c values of x for which there is an integer satisfying this equation, and then we can get what we want. So this is really interesting to have this constant going to infinity with k. Okay. And moreover, the second question, we proved that some equations of this type has infinitely many solutions in positive integers. However, in each case under consideration, we have that the minimum of the power of this set is less than or equal to 3. And the question is how big this number can be. And again, we want to eliminate some trivial solutions of this problem, because if, for example, our set is of this form, then and this value is non-zero, then each representation of this kind implies representation of this kind. So essentially, if A is here, we can take B of this form and get some not interesting, in fact, boring identity of this type. And so we play with computer and found that the minimum of the sets A, B can be at last 5. For example, if we take A equal to 1, 2, 3, 4, 6, and B 1, 2, 3, 4, 5, 10, then this difference of this partitions functions is the product of two quadratic equations, and the one is not interesting, but this second one give infinitely many solutions in positive integers, not so small solutions. Okay, this is interesting because in general if we have equation of the type f equal to g and fg has degree 4, then the corresponding curve has genus 3. So not only finitely many integer solutions, but also only finitely many rational solutions. Okay, and again we have the next problem. We have a partition function counting some combinatorial objects, and so this is a quasi-polynomial, as we said, and this is an algebraic object. But on the other side, this function live in the realm of combinatorics. So it would be really nice to have some combinatorial conditions on A and B, on the sets A and B, which guarantees non-existence or finiteness of integer solutions of the equation PAX equal to PBY. And similarly, again, partitions function count combinatorial objects. So usually we want to have not only proofs which are analytic or just computational, as in some cases, but also combinatorial. So it would be really nice to have some bijective proofs of some identities obtained, which are possible. So okay. And more specific more specific conjectures are the following. We can ask about the solutions of this equation, where we have partitions function corresponding to 1 to up to m and 1 to up to n, and believe that this equation has always only finitely many solutions in non-negative integers. And in fact, I believe that for mn sufficiently larger, there are none. Okay, so this is probably the simplest conjecture to get the general result concerning this particular case. And finally, one can ask about sufficient conditions which guarantees that this kind of equations has infinitely many solutions in different positive integers under the conditions that A and B are infinite and some properties W1, W2. This is still possible, but we have some not really interesting identities like that PA-MN is equal to PBN, where A is just the set of powers of M. Thank you very much.
Thank you very much. We have time if there are any questions, but I look in the chat and the Q&A. So again, thank you very much for your talk. And our next talk will be in 5 minutes.